Hello everyone, welcome to our last press conference today, and it's on impacts of geoengineering on land, oceans, and the atmosphere. And taking part in this press conference we have Ken Caldeira, who is a climate scientist at the Carnegie Institute for Science, Department of Global Ecology at Stanford University in the USA, Helen Murray, who is a researcher at Section for Meteorology and Oceanography at the Department of Geosciences at the University of Norway in Oslo, and Hanel Korhonen, sorry if I'm mispronouncing your names, head of the Atmospheric and Ocean Modeling Group, Finnish Meteorological Institute in Helsinki in Finland. And they will give short presentations and then we'll open the floor for questions. Thank you.
So should I start here?
Yeah.
Hi, so I'm Ken Caldeira from Carnegie Institution on the Stanford campus, and I'm going to assume some familiarity with the basic idea of solar geoengineering, but just to reiterate, the basic concept is that greenhouse gases heat up the planet, and one of the approaches to try to cool things back off is to reflect some sunlight back to space. And there have been a series of volcanoes, most notably Mount Pinatubo in 1991, that demonstrate pretty convincingly that aerosols in the stratosphere are able to cool the planet. And one of the concerns about these proposals have been the effects on the hydrological cycle and the effects that the changes on the hydrological cycle will have on land plants. And most notably, one of the things that many studies have shown is that if with CO2 changes, the ratio of changes in temperature to changes in precipitation are smaller than with changes in the amount of absorbed sunlight. And so if you offset the total amount of precipitation, the total amount of temperature, you end up with less precipitation in a solar geoengineered world. And the concern is, what would that do for land plants? So just to say that there have been previous studies that have addressed this issue. In fact, I think we did the first one more than a decade ago. We also did a study a few years ago in Nature Climate Change on crop yields in a geoengineered climate. And what's new about what I'm doing here is I'm looking at a big archive of model simulations called GeoMIP, and there have been a couple of papers exploring some of the issues that I'm raising here based on the GeoMIP results. And so just to say that there is a background to what I'm doing, it's not all de novo. So forgive the quality of these maps, but basically what we did is we took a model into comparison project, which is known as GeoMIP, which is a geoengineering model into comparison project, along with simulations from CMIP5, which is a climate model into comparison project, and did a multilinear regression on a number of variables. And most importantly for this talk is net primary productivity of land plants. And we looked at which factors affect net primary productivity in the models. And this is, I don't have time to go into methodology right here, but the basic idea is to break the sensitivity of net primary productivity into temperature effects of CO2 fertilization, and effects of the reduction in incoming sunlight. And basically this model is one chosen out of the archive. It happens to be one of the ones that has a stronger response to all of these signals. And basically what you see for the upper left one is the response of the net primary productivity to changes in global mean temperature. And what you see with what the model projects is that increasing temperatures from global warming will lead to increasing heat stress through the tropics and reduce net primary productivity, but that in the northern mid-latitudes, that the productivity of land plants increases, and this is because the warmer temperatures there lead to longer growing seasons. And also that metabolic rates can increase at higher temperatures. The plot on the lower left shows the response to CO2 fertilization in this model. So this is taking just the effect of CO2 without temperature, and basically it shows that there's a strong influence of CO2 that CO2 has a strong fertilizing effect, especially throughout the tropic areas where biomass productivity is strongest. And the lower right one here is the sensitivity, is the sensitivity of this model to changes in downwelling shortwave radiation or downwelling sunlight. And I scaled the color scales, which aren't on here, so that if you were to offset the temperature, that if you were to offset the temperature from the CO2 doubling, these colors represent the approximate contributions of these effects. And so the basic point of this talk is that the temperature influence of CO2 tends to decrease productivity at the low latitudes, increase it at the high latitudes. CO2 fertilization tends to increase it nearly everywhere. The direct effects of sunlight changes are second order. And so the main expectation of decreasing the amount of sunlight to compensate excess greenhouse gases would be to undo most of these temperature effects, and that would tend to have effects of opposite in sign, and so tend to help plants grow in the tropics, but have some negative effects on plant growth in high latitudes. So I'm running out of time. I don't go into method stuff, but just to just show for a range of models, this is just on global mean, shows that almost all the models, the net primary productivity of the land biosphere decreases with increasing temperature, but that different models have different extents of CO2 fertilization and different responses to the amount of incoming sunlight. And so there's still a lot of intermodal spread, which makes these results be suggestive, but certainly not conclusive. Let me just go to this one here. Just this now to show from the South Pole to the North Pole for 4 different models. This is the effect of increased CO2, taking into account the temperature effect of the CO2 increase on plant productivity as a function of latitude. And then the right side is for an equivalent reduction in incoming sunlight, what would you expect that to do to plant productivity? And this is the model that I showed you before, which is the most dramatic response of the ones I looked at. But again, showing that the effect of reducing temperatures, allowing the low latitude production to increase, overwhelms the negative effects of less sunlight to drive photosynthesis. But even though there's a lot of scatter between models, there is a general pattern of positive values in the tropics, although not uniformly positive, and also negative values in the high latitudes, where the cooling temperatures make shorter growing seasons. And so I think there's a general trend. I think I ran out of my time, but that I think let me just run to the last line here. The CMIP5 models provide a basis to expect that deflection of sunlight would increase land plant productivity in the tropics and decrease productivity in the high northern latitudes, but much uncertainty remains. I'd say there's a lot of intermodal spread. Okay, thank you.
I'm Helen Muri from the University of Oslo. I'm talking about cirrus cloud thinning, climate engineering, and in particular the climate response during the northern hemispheric summertime. So cirrus clouds, first of all, there are these high, thin, wispy-looking ice clouds that appear in the upper troposphere, and they have a net warming effect on the climate as they trap long-wave radiation. So the concept of this climate engineering method is then to try to thin out and remove these clouds such that you could radiate out more long-wave radiation at the top of the atmosphere. So the theory is that you could seed then the upper troposphere with small particles, and these particles would have a particular nucleating properties such that they could start the freezing at cold temperatures, but lower supersaturations with respect to ice than freezing would occur at otherwise. So by introducing these particles, you could, in theory, nucleate out fewer but larger ice crystals that would grow heavy and then eventually precipitate out of the clouds and reduce cloud lifetime. So we did some experiments with the Norwegian Earth system model. First of all, just a basic pre-industrial control run, and then a run where you instantaneously doubled the pre-industrial carbon dioxide concentrations, and a third climate engineering simulation where you simultaneously double the CO2 concentrations at the same time as you're applying the Cirrus cloud thinning at a magnitude to offset the radiative forcing from the doubling of the CO2. And the Cirrus cloud thinning was implemented by simply increasing the fall speed of all ice crystals at temperatures colder than minus 38 degrees, as this is typically Cirrus forming temperatures. So there we looked at the climate response during June, July, August, September. Top right figure shows the cloud amounts, or the amounts of high clouds in the pre-industrial run, where you have the most clouds in the tropics and the southern hemisphere towards the pole. Bottom figure shows the resulting reduction in the high cloud amounts from the Cirrus cloud thinning, where there's a reduction of the high clouds at all latitudes, but particularly strong in the southern hemisphere towards the pole. And the resulting net cloud radiative forcing is shown on the top left figure, where there's an overall reduction in the cloud forcing, but the strongest is in the southern hemisphere, as you have less compensating shortwave effects, because the cirrus clouds, they do reflect some incoming shortwave radiations of sunlight, which acts to cool. So when you're thinning out the clouds, you're reducing this cooling effect. But this is southern hemispheric winter time, so you have less solar radiation, so this compensating effect is smaller there. Looking at resulting surface air temperature changes, top right figure shows how much the cirrus cloud thinning is cooling compared to the doubled CO2 run, where there's a cooling everywhere. Global means about minus 1.8 degrees during June, July, August, September, and you reach as much as minus 5 degrees southern hemispheric low latitudes, high latitudes rather. And bottom figure for reference shows the warming from the doubling of the CO2, whilst top left then shows the cirrus cloud thinning compared to the pre-industrial, where the global mean change is 0 more or less, but you have an overcooling in the southern hemisphere because this method is most efficient there during this time period. There's also residual warming then in the northern hemisphere because of the compensating shortwave effects and also stronger carbon dioxide warming. So you're then increasing the thermal gradients between the hemispheres. So let's look at what this does to the hydrological cycle. Well, the most prominent feature is the northwards shift of the intertropical convergence zone. So this is this heavy convective rainbound around the tropics and equator. So this then moves away from the colder hemisphere and then more into the warmer hemisphere, and also pushes the precipitation more onto land, including over the Asian monsoon areas and also the drought-sensitive Sahel areas. There's also an increase in the moisture budget of much of the land regions, and that's because you're thinning out the ice clouds, so you're letting more shortwave radiation reach the surface, so it's facilitating for more convective activity at the surface. So just to sum up, you can achieve a cooling from the cirrus cloud thinning at magnitudes to globally offset the warming from a doubling of CO2, but you would end up with a different climate, however, due to the heterogeneous nature of the forcing that you're applying. including then the northwards shift of the rain into the warmer land areas and intensification of the monsoons.
So my name is Hannele Korhonen. I come from the Finnish Meteorological Institute, and I'll summarize our recent climate model study on what would be the climate impacts of large tropical volcanic eruptions if they took place during stratospheric geoengineering. And I'll start with the main findings. So our first main finding is that even though such an eruption might have relatively small global impacts, the regional impacts probably would be quite significant. We find cooling in the tropics as we would expect, but then quite surprisingly warming in the northern latitude, the northern hemisphere mid-latitudes and the southern hemisphere high latitudes. In this specific scenario that we simulated, we found 0.5 to 1 degree warming over large regions of Eurasia and North America, and up to 1.5 degree warming in some parts of the Antarctica. And in terms of precipitation, we found significant decreases of the order of 0.5 millimeters per day in Southeast Asia and Central America, and corresponding increases over the tropical Pacific. I should say, though, that these specific numbers are dependent on the scenario. And our second main finding was that the observations from previous eruptions into the current atmosphere that isn't climate engineered, they cannot be directly used to reliably predict what these effects of the eruption would be during climate engineering. This is because we see quite significant regional differences. And I'll illustrate them here. So on the top row, we have the temperature change due to the eruption during the 1 year following the eruption, and in the bottom row we have the precipitation change. And now on the left-hand side we have the case when the eruption takes place sort of in the current atmosphere, where there's no climate engineering, and on the right-hand side where the eruption happens during climate engineering. And I really can't show you with the pointer, I don't know if you can see this screen, but in this climate engineering case, for example, there's significantly less cooling over the tropics, and then, as I already mentioned, there is quite notable warming in some parts of the world that is lacking in the other simulation. And similarly, for the precipitation change, we also see clear differences, especially in the tropics. If you look sort of east from Indonesia, you see that these precipitation change, the sign is actually reversed. So where we would have decrease in precipitation in current atmosphere, we actually see increase in the climate engineered atmosphere, for example. Before I tell you why this happens, I'll give you a little bit of background so it's easier to understand. So what happens after an explosive eruption is that a large amounts of sulfur dioxide is released into the stratosphere, and it is then oxidized to form sulfuric acid, which is a very reactive molecule. It doesn't like to be alone. So it clusters with other sulfuric acid molecules and forms new aerosol particles. And once these particles grow in size to about 200 nanometers or so, they start scattering solar radiation and reflect some of the solar radiation back to space, and therefore cool the Earth's surface. And now, in fact, this observed cooling is the sort of inspiration for the whole idea of the stratospheric climate engineering. There, the injections of sulfur-containing species would be done deliberately. So why do we see different climate impacts after the eruption if it happens during climate engineering? It's because the fate of this sulfuric acid that is formed is different when it takes place during climate engineering. In a sort of the current atmosphere, the sulfuric acid would form predominantly new particles, whereas in the climate engineered atmosphere, it would condense onto pre-existing particles from these climate engineering injections and grow them in size. So we would end up with fewer additional particles, which would be larger. And this kind of a population would be a less efficient scatterer, but also because the particle size is larger, they would sediment faster out of stratosphere, and their lifetime would be shorter. Now, the reason why we saw this regional warming in some parts of the world is that it would be very likely that climate engineering would be stopped after the eruption, and this is what we also assumed in our simulation. So far away from the eruption site, which in our case was in the tropics, the particle load would start to decline. And then compared to the pre-eruption climate, you would have less cooling particles and therefore a warming impact. And I'll wrap up by reminding that these numerical values that I've shown are scenario specific. So the actual regional climate impacts would depend on the magnitude of this eruption, but also on the location of the eruption. And we've used here a Pinatubo-like eruption in our case. It would also depend to some extent on the magnitude of the climate engineering injections and also sort of the climate system state at the time of the eruption. This is often referred to as the internal variability of the climate. So what we've done here is that we have made 10 different simulations, all with different initial states, and what I've shown you are the mean values from those 10 different simulations. But obviously, in the real atmosphere, you would only have this one specific state, and also in our simulations, you see differences between these different simulations, especially outside the tropics. So there might be regional impacts that aren't captured by the mean. Thank you.
Thank you very much for your presentations. We'll now open the floor for questions. Are there any questions?
Hey, Liz Gallagher from Environmental Research Web. I've got a question for Ken, which is what do your findings mean for any potential application of geoengineering?
It's a rather broad question. The way I would characterize the findings is, at least my analysis of this GeoMIP archive indicates that there's some expectation that if solar geoengineering were applied, that you would expect plant productivity to improve in the tropics and get worse in the northern high latitudes. And I think, so first of all, I'd like to stress that this is a highly uncertain result. Well, it's common to many models. It's not seen in every model, but I think it's at least an expectation. So the first thing I would say, it would be useful to do some more research to try to see how robust this result is. But sometimes this solar geoengineering has been presented as a way for the first, for the rich countries, something that they might do to keep the oil and coal industries going, and that the poor countries of the South would be the ones that would suffer. But I think the results of the models indicate that the likely sign of impacts likely to be the reverse of that, that at least if plant productivity is the concern, that it's probably the poor tropics that would stand to benefit and the rich north that would stand to lose. But again, I would call these very preliminary results that need further investigation, and they're not common to every model, although it is a general trend seen in the models.
Are there any more questions? Okay, if not, we'll finish. Oh, wait, there are.
My name is Odd Pilström. I'm a freelance writer. Given the prospect that global warming might be worsening as time goes by, it's a question for all of you. How probable do you think that geoengineering will be? What's the chance of such means being taken into practice?
Who wants to start throwing out numbers? It's a very difficult question, isn't it? Yeah.
I'm happy to babble on, but I don't want to dominate this. So if you want to,
perhaps you want to comment first, and then we can.
Okay, so I would say different days that I wake up, I have different subjective probabilities that and I think a lot has to do with how bad climate change will end up being. That my central expectation is that we will muddle through, that humans already live from the equator to the Arctic Circle, and that we're quite adaptable as a species and will whatever climate throws at us, we'll muddle through. On the other hand, if you look at the business as usual, say RCP 8.5 projections for this summers or near the tropics, almost every summer will be hotter than the hottest summer yet on record, and many of these summer extreme heats are associated with crop failures. And so there's not a major, not the expectation, but there's at least some possibility that there would be widespread crop failures throughout the tropics. And I think if that occurs, the pressure and this kind of evidence that I'm showing today, that there's some expectation that plant productivity would be increased through the deployment of a solar geoengineering scheme. That, and then I guess the third element is that transforming an energy system takes many decades before you see any climate benefit, and the main climate benefit is the slowing of warming, not the actual production of cooling. And so the only thing a politician can do to actually start the planet cooling within their term of office or within their political career is one of these solar geoengineering things. So I think if we have a couple widespread crop failures, institutional failures that fail to feed this hungry people, developing world leaders who want to see their people with food, I think the pressure to deploy one of these proposals could be extreme. And so I would say my central expectation is that they never get deployed. But I think if this extreme catastrophic outcome does occur, which I don't expect it to occur, but if it does occur, I think the pressure to deploy a scheme could be overwhelming.
What about the Arctic, which is the warming in the Arctic is 2.5 times the global general speed. And you have feedback mechanisms in the climate system. And there are some alarmists out there that have said that it's urgent to get geoengineering into practice to prevent further speed up of the warming in the Arctic. Do you have any comment on that? Any of you?
I'm willing to babble on any topic, so
Go ahead.
I'll go babble on this one. So, this is my just personal view without any basis in any empirical fact whatsoever, is that I think it's unlikely that a solar geoengineering system would be deployed in a situation where people's lives aren't at stake. That I think there's too much controversy over it to I don't think, to protect the polar bears or something. Now the question is, let's say methane starts pouring out of Siberia, which again is not something I expect, but it's not something that could be ruled out with complete certainty either. Would that be enough to cause countries to deploy a scheme? I don't know. I guess we're really in the realm of speculation there, but it would have to be a huge, general consensus that there is some imminent climate crisis. But even then, I guess there is the example of the Montreal Protocols where countries acted in the face of a threat that was projected through models and so on. And so you could think of it as analogous to a Montreal Protocol type thing, although it's obviously more interventionary. So I wouldn't rule it out, but I think the most likely scenario is one where people's lives are at stake, and I would think it would be much harder to get consensus for a purely physical climate system feedback.
Can I just comment that I don't disagree, but you seem to trust very much that there is going to be a consensus and nobody starts it sort of like one nation, for example. Because it could be implemented only by one actor.
Yeah, well,
consensus.
I don't necessarily believe the one actor one, just because, but we did a paper on coalitions around solar geoengineering, and this is true. I think you can use, for a negative example, the invasion of Iraq, where it doesn't take, maybe not one actor, but you can have a small coalition of powerful enough countries they can do something and nobody else can stop them. And so That's right, it doesn't have to be a consensus, but you'd have to have at least consensus among enough powerful people.
I think if you look at the emission pathway that we're currently on, we're overshooting RCP 8.5 at the moment. So I think with the greenhouse gas emissions that we have already made, with that we're already committed to a certain amount of climate change, and as you say, a large part of that will be happening in the Arctic. But if we're going to implement solar radiation management to save the Arctic, I think you're then introducing so many more further risks. So, yeah, they are both good points that you don't necessarily have to be a consortium agreeing on implementing it. There could be, of course, be solo or rogue actors doing it. But I think then you're getting into very political territory, and also I think you're getting into more sort of war territory where that's a more likely outcome than the actual long-term sustained implementation of solar radiation management.
Just as a point of information, I was on the National Academy panel in the U.S. that recently produced a pair of reports on climate intervention approaches, and we examined this rogue actor scenario, and the basic conclusion of that panel was that the individual sort of rich person or tiny little country can't really, could in principle do it physically, but there's enough mechanisms for powerful countries to stop them. If nothing else, you can cut them off economically, bomb them, etc. But this other scenario where you have a small coalition of countries doing it is plausible.
Luis Lidón from the Spanish news agency EFE. Knowing that we have the technology to change or to fix climate, could that be a distraction from effectively reducing the green gases? And could that be the largest negative side effect of this kind of studies or technology?
Well, you can see it as a distraction that you think, okay, you can cool the climate through these methods. You can just keep emitting greenhouse gases. But the way I like to see it is that all of these modeling experiments, they're more highlighting all of the new risks that could be introduced from the solar radiation management, and looking at those risks, then the safest option is, of course, to reduce greenhouse gas emissions and to aim for a more sustainable way of living and managing the planet.
There have been a number of social science studies that have now been published where people took focus groups, asked them how much they'd be willing to do to reduce emissions, told them about these solar geoengineering proposals, and then asked them again at the end. And I believe that all of these studies have found that people's willingness to act on emissions reduction increased after hearing about the solar geoengineering proposals. And that's, I think the logic is that, if the scientists are, really the research into this is an act of desperation on the part of the scientists, in that people see the greenhouse gas concentrations increasing, and people are looking at are there other ways to reduce environmental risk. And I think people think, well, if the scientists are so desperate that they're looking at these crazy kind of proposals, maybe we should take this risk seriously. And so I've seen this happen where people, it's in a little bit, sometimes nuclear power plays a similar role, where there are people who don't like the idea of climate change, and they think people are toying with the models to get any result they want. And you say, well, look, I don't really like this idea of solar geoengineering, but the models say it would reduce the amount of climate change. And the same thing when similar thing happens with nuclear power, where people who like nuclear power but don't like climate change start thinking, well, if climate change helps motivate nuclear power, maybe it's not so bad. And so I've seen people who didn't take the climate change problem seriously use, I don't know, solar geoengineering as kind of a gateway drug to kind of get them to take climate models seriously and the climate projections seriously. Because if you're willing to trust the climate models when they say solar geoengineering works, well, then you should trust the climate models when they say that greenhouse gas emissions are dangerous.
Thanks very much. Are there any more questions?
My name's Lewis Collins. I'm an editor at Nature Communications. I have a question for Ken. Regarding your models, how do they take into account different types of vegetation? So can they tell if crops in, say, tropical rainforests are reacting the same way to these changes in parameters? Or is that even a point or not?
These models represent mostly natural ecosystem types, and so do not specifically relate to crops. We did a study a few years ago with just 2 climate models with an embedded crop model that found similar results. And the basic conclusion is fairly robust, that most crops and most plants benefit from added CO2, but heat stress damages and slows growth near the tropics, whereas warmer temperatures tend to give longer growing seasons at the high latitudes. And so, and those basic principles apply both to natural ecosystems and to crops. And so there's a set of crop models has not been run for the full suite of models that I showed today.
Do we have any more questions? Okay, if not, we'll finish here. This is our last press conference today. There is a great debate at 3:30 on the 10 billion are we managing, and that's in Y1. And the press conferences are back up tomorrow at 9 a.m. with an update on Iceland's Bárðarbunga volcano. Thank you. See you tomorrow. Bye. Thank you very much.